Dear learners, welcome to second week, first lecture. So, in first week, we have done that basic definition of cell geometry, derivation of first fundamental forms and derivation of second fundamental form. Surfaces. So, in last week we have derived that definition of a curvature, normal curvature Kn can be written as dn hat dot dr and dr dot dr, whereas this numerator term is known as second fundamental form and denominator is first fundamental form. If we say that divide by d alpha top and bottom, then it reduces to equation 18 and we define that d beta by d alpha is lambda. So, if we differentiate with respect to equation 18 with respect to lambda and equate to 0, ultimately it reduces to a quadratic equation and solution of quadratic equation gives you the two roots. These two roots are extreme values of normal curvature K1 and K2 and these are known as principal curvatures. If we are interested to find out the principal radii, then we can say that R1 is nothing but 1 upon my K1 and R2 is nothing but 1 upon my K2. But the formula written here is valid when the parametric or our principal curves are orthogonal to each other, which I have written. So, how to deduce this? In that case, lambda is 0 must satisfy the principal curves. So, for that case this equation becomes like 0 and from the equation of normal we get this equation where h should be greater than 0. So, if principal curves are orthogonal, then f will be 0 and m will be 0. So, this will give you nothing. So, ultimately in the principal curves, if we say that f is 0, n is 0 and it reduces to equation 20. So, we cannot reduce from the previous equations just putting d beta is 0 or alpha is 0, we have to set like this and now from this equation we say that over the curves where beta is constant and alpha is constant. So, for constant line d beta is 0. If d beta is 0, so K1 becomes L by E. For a constant alpha lines, d alpha is 0 because there is no change in alpha for a constant alpha line, that gives you n by g. So, through this assumption we can get for where principal curvatures are orthogonal to each other, we can get it L by E and n by g. Now, we are going to find out the derivative of unit vector along its parametric lines, which are very important. Basically, these derivatives help us to frame up some more theorems which are ultimately used to develop the fundamental equations for the surfaces. So, we have 3 orthogonal unit vectors. If I say like this, here my surfaces, you may assume in an direction alpha and beta. So, beta is increasing here. So, at a particular this here beta is constant and alpha is increasing here. So, on a particular line here alpha is constant. Like no need to worry about that, like x and y. If we have a grid system, what is that? A line here, x values remain constant. So basically over here x is constant. If we draw like this, over here y value is constant. Okay, the same way we can say that here on which line it is going. So perpendicular lines, beta value will be constant, and here alpha will be constant, means alpha 1, alpha 2 and so on. So we consider three mutually orthogonal unit vectors T1, T2 and n hat, where T1 is tangent vector along line 1 and T2 is tangent vector along line 2 and n hat is the surface normal that are oriented on a surface at a given point. T1 and T2 are tangent to alpha and beta directions, which I have said that first line and second line of curvatures, and n is the normal to the surface. So as this triplet of unit vector moves over the surface, because if we move from one point to another point, definitely some different tangent can be defined. So the direction of these unit vector changes, however their magnitude still remains unity, but they still change orthogonal to each other. If you remember that very initially I said that in a circle, that if it changes from here to here, so its tangent vector changes, so its sign is changes. So T1 can be defined as r comma 1 upon magnitude of r comma 1, that is basically magnitude of T1. So this magnitude is nothing but definition of A1. A1 is what? A1 is our Lamé parameters. Same way T2 hat is r comma 2 divided by magnitude of R2 magnitude. So r comma 2 derivative upon में A2 is Lamé parameters, and then n1 can be T1 cross T2 n hat R1 cross R1 comma 2 A1 by A2. So assuming that parametric curves are principal curves and they are orthogonal, so we can find out the derivatives of surface normal and derivatives of even tangents, since very starting that n1 comma 1 n hat comma 2 are perpendicular to n hat. They must lie in the tangent plane formed by T1 and T2. So this is very important frame up, that n hat derivative 1, n hat derivative 2 will be perpendicular to n, and they will be lie in the tangent plane T1 and T2. If this is the condition, then we can write that n comma 1 will be some coefficients A into T1 plus B into T2, because they lie in the plane of tangent plane, where A, B represents the projection of n hat comma 1 on the plane T1 and T2. Now you multiply this equation with T1 hat. If you multiply with this equation with T1 hat, so T1 hat dot T1 hat it becomes 1, and T2 dot T1 it goes to 0. So basically this term will go to 0 and it remains 1A, and from here T1 dot n comma 1, T1 we know r comma 1 upon A1 and n comma 1 upon A1. So basically this is the definition of L upon A1 is equal to A. Same way, if we multiply with the T2, then this gives you r comma 2 dot n comma 1 upon A1, and from here this is going to be 0. So B times equal, but this is the definition of M. So, for a orthogonal system, that is going to be 0. So, from these two equations, B comes 0 and A comes L by A. So, we can say that n comma 1 can be L by A into T hat 1. Now, we will further simplify it. If R1 is equal to 1 upon K1, radius of curvature, and that can be written as E by L, and E is square of Lemma parameters. So, L by A1 from here, R1 is here and A1 goes from here. So, A1 by R1 is equal to L by A1. So, L by A1 can be written as A1 by R1 in terms of Lemma parameters and radius of the curve. So, in this way we will get equation that n comma 1 will be A1 by R1 into T hat 1. By following the same procedure, so I am just going to drive it here. Let us say n comma T2 hat is C times T1 hat plus D times T2 hat. Now, you multiply this equation T1 hat, that gives you C1. If you multiply this equation with the help of T2, that gives you D, let us say 2 and 3, because we know that T1 and T2 are perpendicular to each other. Then T1 is R comma 1 upon में A1 n comma 2 is equal to C, and this one is R comma 2 n hat comma 2 upon में A2 is equal to D. These are orthogonal to each other curvilinear parameters. So, this is going to be 0. So, C becomes 0. From here we can say that D is nothing but n by A2. Now, using the concept of K2 is equal to 1 over में R2 something Lmn n by G, and from there again n can be written as like f by G. So, f becomes A2 square upon में n. So, from there using those concepts we can derive that A2 by R2 and T hat 2. So, the surface normal derivative along one direction can be written as A1 by R1 into T hat. A1 is a Lemma parameter which is very easy to calculate, and R1 is the radius of curvature. So, these two equations, differential equations, are known as theorem of Rodriguez. So, we can write these theorems, and they are very useful to developing the theorem for surfaces. Now, we can derive some more relations, that let us say dn will be n comma 1 d alpha, n comma 2 d beta. So, n comma 1 can be replaced with the help of this, and n comma 2 can be replaced with the help of theorem of Rodriguez. So, that gives the derivative of unit normal vector surface 2 along the principal parametric curves. Very first theorem is theorem of Rodriguez. So, the starting one is that derivative of surface normal will lie in the plane of T1 and T2, and using the simple mathematics multiplying with T1 hat and T2 hat we can find out the basic relations. Now, we will find out the derivative of T1 hat and T2 hat. First, we will consider that T1 is this, already we have defined this r comma 2 and A2. Now A1 T1 r comma 1, A2 T2 r comma 2. So we can say that r comma 1 2 r comma 2 1, which is basically that mixed derivative of d beta by d alpha. If you change the order, it does not matter, that position vector. So r comma, we can write that r comma 1 whole ka derivative 2 equal to r comma 2 whole ka derivative 1. R comma 1 can be written as A1 T1 hat, r comma 2 can be written as A2 T hat. So differentiation of first function, it will becomes A1 comma 2 T hat remains, plus first function as it is, differentiation of second function T hat 1 comma 2 equal to differentiation of A2 comma 1 and T hat 2 remains same plus A2 T hat 2 1. So from this equation we can find out T hat 2 comma 1 can be written as this equation, and T1 comma 2, if we in some other sense, that from there it can be written as that. We know that T comma 1 equal to dt 1 upon me d alpha. T comma here 1 comma 2, 2 comma 1, 2 comma 1, 1 comma 2, we want to use it, and 1 comma 2 dt hat d beta and so on. Same way you see that terms are here 1 comma 2, what are these, and 1 comma 2, 2 comma 1, 2 comma 2. So A comma 1 means d alpha by A1 by d alpha, 1 comma 2 means with the respect to beta derivative, 1 means alpha and beta and so on. So again T1 hat comma 1 and T1 hat 1 comma 2. So we have a, let us say, vector T1 hat and its derivative T1 hat comma 1 and T1 hat 1 comma 2. They will be perpendicular to this and they will lie on the plane of n hat and T2 hat. So this is our starting. So let us say we frame up equation again, T hat 1 comma 1 equal to A n hat plus B times T hat 2, where A and B represents the projection of T hat 1 comma 1 on n hat and T2 respectively. If you multiply this equation with T2, that gives you basically T hat 2 dot T hat 1 comma 1 gives you B. From this it gives you n hat dot T 1 comma 1 A. This is going to be 0 and this is going to be 0. So this I have written and this equation is here. Now T1 and T2 are perpendicular to each other, so their product will be 0. So from there we can set up another set of equations that T2 comma T1 whole derivative 1 can be written as 2 comma 1 1 plus 2 comma 1 2. So this term which we are using here can be written as minus T2 comma 1 and T hat 1. Now we want to know what is T hat 2 comma 1. So just in the previous we have written T hat 2 comma 1. So we will use this equation here and multiply with T hat. So T hat it will give you 1, this term will vanish and again 1 comma 2 it is also perpendicular to T1. So, it gives you only the contribution of this term. So, B is nothing but A1 comma 2 upon में A2. Again using n dot, because surface normal and T1 are again perpendicular. So, their dot product is going to be 0. So, taking differentiation with respect to 1 gives you this equation. And if I further find it out that n comma 1 T1 can be written as n T1 comma 1. So, A into, in this equation we need n comma T1 comma 1. What is the substitute of that? N into T1 comma 1 substitute is n comma 1 T1. N comma 1 from the theorem of Rodriguez, A1 by R1 into T1 hat dot of T1. It gives you 1. So, A becomes minus A by R1. If you substitute all values, then T1 comma 1 can be written as minus A1 upon may R1 n hat minus A1 comma 2 upon may A2 into T2. So, derivative of tangent vector along the first direction can be represented like this. Same way we can derive the derivative of tangent vector along the second directions. So, they will also perpendicular to T1 and they will lie in the plane of n and T2. Now, you multiply with the T2 and n hat. So, from there you again get equations D and C like this, and using the concept of n dot T1, now this time taking derivative with respect to 2. For deriving the previous equation we have taken the derivative with respect to 1. So, again n comma 2 using the theorem of Rodriguez can be represented like this. Now, you see that T2 dot T1 is, they are perpendicular to each other. So, it is going to be vanish. So, C is going to be give you 0. Now, we are interested to find out D. So, we have to replace that equation of 1 comma 2 and multiply with the T2, that will give you the value of D. So, here D comes A2 comma 1 upon A1. So, T hat 1 comma 2 gives you this equation A2 comma 1 upon may A1 and T2. So, in this way we get these two equations. Similarly, following the same procedure, we can get T hat 2 comma 1 and T hat 2 comma 2. Again we can say that, let us say T hat 2 comma 1 will lie where? Plane of T1 hat and n hat, and following the similar procedure. Then same way T2 comma 2 also will lie on the same plane. So, we will get similarly two more equations which are written here, that T hat 2 comma 2 can be written as minus A2 by R2 n hat minus A2 comma 1 upon may A1 T hat 1. Then T hat 2 comma 1 A1 comma 2 A2 T hat. So, these four differential equations, they are giving you the relation of derivative of tangent vectors along the parametric curves 1 and 2 can be represented in terms of Lamé parameters and radius of curvatures. So, these four formulas are known as Weingarten formulas, and these PPTs were prepared by our MTech student Vaibhav Raman. Now, we have theorem of Rodriguez and Weingarten formulas. Why we have derived this? What is the use? Actually, these formula will help us to derive theorem of surfaces. So, these are very much required to develop the differential equation for theorem of surfaces. So, in that process we need these formulas, these are standard formulas. So, once you know that okay, these three vectors T n hat, T1 and T2, and using their relations we can find out derivative of n1 comma 1, derivative of not 1 comma 2, same derivative of 1 comma 1, derivative of 1 comma 2, derivative of 2 comma 1, derivative of 2 comma 2. Fundamental theorem of theory of surfaces, we are interested to find out three differential equations that relate the quantities A1, A2, R1, R2 of a given surface. These equations are used to ascertain whether an arbitrary choice of these four parameters will be define a valid surface or a real surface. So, to derive these relations we will going to use the second a mixed derivative of unit vectors. So, to derive the Cauchy equations we are going to use this relation, that mixed derivative n comma 1 2 equal to, we write n hat at least, n hat comma 2 1. So, we can say that n hat comma 1 derivative 2 equal to n hat comma 2 derivative 1. Now, n hat 1 using the formula of Rodriguez we can write like this, comma derivative 2 and A2 by R2 T hat 2 derivative of 1, and then differentiate with respect to 2. So, first function derivative with respect to 2 T hat 1 plus first function as it is derivative of 1 comma 2, then A2 by R2 derivative 1, T2 remain as it is, and then next time using the chain rule of differential, that first term as it is, differentiation of second term. Now, we know that what is T hat comma 1 2 and T hat comma 2 1. So, using the Weingarten formula, T hat 1 comma 2 1 is A2 comma 1 upon A1 into T2. T2 comma 1 is equal to A1 comma 2 A2 upon में T1. If we substitute is like this, and now collecting the coefficients of T1 and T2. If you arrange, or you can let us take from all left hand side or right hand side, then it is going to be 0. Now, the question is that T1 cannot be along the line T2, they are perpendicular to each other. So, the relation will be valid only if their coefficients need to be vanish. So, if we are saying that is going to be 0, so A1 upon में R1 whole का derivative 2 can be written as A1 comma 2 upon में R2. Basically, this equation gives you A1 upon R1 whole derivative 2 will be written as A1 comma 2 divided by R2. From this we can get is A2 by R2 derivative 1 can be written as A2 comma 1 upon में R1. So, these two differential equations gives you the relation between A1, A2, R1, R2 and known as Cauchy equations or Gauss-Cauchy equations. Generally, it is known as Cauchy equations. Later on, the Gauss equations will come up. Now, we are going to use the mixed derivative of tangential vectors 1 comma 1 2 and T hat 1 comma 2 1. Same way that T hat 1 comma 1 whole derivative 2, 1 comma 2 whole derivative 1. Now, using the formula of Weingarten 1 comma 1 is this much and 1 comma 2 is this much, and taking the derivative. That gives you this big equation in which we have a coefficients of n comma 2, t comma 2 comma 1 or if we use that n comma 2, use the theorem of Rodriguez here and theorem of Weingarten here, then again theorem of Weingarten here. So, if we substitute these values, so n comma 2 is A2 by R2 into T2, T2 comma 2 is this much and 2 comma 1 is this much. So, this is a big equation and all things are taken as the left hand side and equated to 0. Here you see that equation to satisfy the coefficient of n hat, T2 hat and T1 hat, all they are perpendicular to each other. This equation will be valid only when its coefficients will vanish. So, from saying that coefficients of T1 will give you this equation, then coefficient of n hat will give you again Cauchy equations, and coefficients of T2 gives you the Gauss conditions. That if you equate the coefficients of T hat to, that gives you the Gauss conditions where minus A1 A2 upon में R1 R2 equal to 1 comma 2 upon में A2 whole का derivative 2 and A2 comma 1 upon में A1 whole derivative 1. So, these 4 quantities can be related no more than these 3 homogeneous equations, and if they are to possess non-trivial solution, then we can say that the role of Gauss-Cauchy conditions gives you the fundamental theory of surfaces, and this term is known as Gaussian curvature, and based on this Gaussian curvature we classify the cell surfaces, whether it will be a anti-elastic, synclastic, or it will be a regular surface or developable surface based on this Gaussian curvature. So, now we have known that this Gauss conditions, Cauchy conditions are very important. Now, if E, G, L and N, this E and G comes from first fundamental form, L and N comes from second fundamental forms. If they given as a function of a real curvilinear coordinate system alpha and beta and sufficiently differentiable and satisfy the Gauss-Cauchy conditions, then we can definitely say that there exists a real surface which will have first and second fundamental form like this: E d alpha whole square plus G d beta whole square, first form, and second form will be L d alpha whole square plus N d beta whole square. This surface is uniquely determined except its position in space. So, if they satisfy this all the conditions, so our surface is uniquely determined. Next, Gauss-Cauchy conditions, also known as compatibility conditions of the theory of surfaces. If the surface is not satisfy those conditions, there may be a crack. So, principal curvatures are also its parametric lines if they satisfy the Gauss-Cauchy conditions and they are orthogonal to each other. With this I end lecture 1. In the lecture 2, we will study the different surfaces, the classification of cell surfaces.